Hello, fellow hams and YouTubers. Well, I occasionally like to do a little CW, and I've got the Kenwood TS440, and over here I've got a Yaesu FT817, and down there I've got a straight key and a set of paddles. Now the Yaesu has a built-in keyer. The TS440 does not. So I generally leave the straight key plugged into the 440 and the paddles plugged into the Yaesu. You know, and I use paddles when I'm on the Yaesu and straight key on the 440. But there's been times where I've wanted to use the straight key on the Yaesu, and I got to reach around back there and switch things around and cable-wise, and then change a setting on the Yaesu, you know. And there's been times when I wished I could use the paddles on the Kenwood. So I'm going to solve my problem by building a keyer. Obvious answer, right? An outbound keyer means just a single cable to each radio, and it's all real simple, right? I could pick one up. I've actually got an old Heathkit Micromatic keyer sitting over there in a box. I'm going to do a video on it. I found it in my dad's basement. It's covered in dust. I wonder if it still works. We'll find out. But I want to build one because I have some ideas and I'd like to solve all these problems at once and have some features to it. So the first thing I did was designed it up here. You know, I thought about what I wanted to do. I want to be able to use either the straight key or the paddles at any time on either radio without having to switch any cables around. Since a keyer is going to be computer controlled in a way, I'd like to be able to do keyboard CW as well, type, you know. And so I think I'm going to do my keyer with this little bitty Arduino Nano. Let's see how small that guy is, tiny. Now I've used one of these before in my Arduinovox, my rig interface, which is this silver box here, clone of a SignalLink USB interface. And the Arduino does the Vox keying in it. I've used an Arduino in an opening sequence that I'll use for this video, where I had it drawing on my oscilloscope as I sent CW. And I've used one to demonstrate how diodes are used to steer RF in radio circuits. And I'll link that video below. It's interesting. Check that one out. So I'm no stranger to using the Arduino. I learned how to program the Arduino when I did the Arduinovox. I had no programming experience with it at all at that point. And I'm still learning. And this will be a good way to challenge myself. I'm going to write the software for the keyer from scratch. There are several Arduino-based keyers already out there. I've gone and looked, and there's a few of them to choose from. So I could just easily download somebody else's software, dump it in it, and be done. But I think it's more fun to write the software. Plus, I have an idea that I think is going to make it a little more flexible with the keyboard CW. You see, when you plug an Arduino into a computer, Mac, Windows, or Linux, it creates a serial port. And it can talk to that serial port, and it can take input from that serial port. That's how you program it, right? For Windows, you have to install a driver. I'm not sure about Mac. For Linux, it just shows up. You just plug it in and it's there. So one of the things I'm going to do in my software is the keyboard CW support, so that you could connect a terminal program like Hyperterm in Windows to that serial port this creates, and then type and have it send CW. So yeah, I'm going to use the Arduino. And I guess the first thing we got to do is sort out the hardware, which is the tedious part of the build for me. The software is going to be fun, but I got to make the hardware. So I'm going to use an Altoids tin. Let's go down to the bench and we'll put together the hardware. It looks like everything is going to fit nicely in the Arduino tin. I've been thinking about it, and I got things laid out the way I think it's going to work out. The Arduino is going to be here, and there's going to be a hole over here where the USB port will stick through. That's for hooking it up to the serial USB to the computer. That's going to power it. You could use a USB charger. You know, real simple then to power this keyer without a special wall wart or anything else. This is an 1/8 inch mono jack. This will be the output, the keyed output that will go to your radios. This is an 1/8 inch mono jack that will be an input for the straight key, and this is a stereo 1/8 inch jack that will be the input from the paddles. And this is a 10K pot that will be used to adjust speed. I'm going to just set up the software for a speed from 5 to 30 words a minute. The nice thing with software and doing this all on an Arduino is that you can tweak and change things later very easily without having to rewire stuff. So I'll be able to change weighting and features and everything all through software. It'll be kind of nice. And in fact, I could eventually even come up perhaps with a keyboard interface that lets you quickly do things like change weighting or something. Who knows? You know, it's going to be very flexible using the Arduino. So that's the basic hardware layout. Well, here it is. Everything's mounted and wired up for the super simple keyer. I got to put a knob on here. I'll go dig one up and press that on there. But we've got the Arduino in. We've got our speed control here for 5 words per minute through 30. Input for the paddles coming over here to 2 of the digital input pins. Using one of the analog pins for the speed sense. We have ground and 5 volts on the opposite sides of the pot. So over this way is ground, over that way is 5 volts going to the analog pin, and that's how we'll set their speed. Paddle input here, straight key input. Now the straight key input just goes right over to the keying output, so the straight key just basically shorts the output, just passes through. Keying transistor is right here. Get in shot, Kevin. Got a 1.5K resistor coming from D13 to the base. I use D13 because it has an LED on board up here that's in series with that data line. So while I'm testing, I'll have a nice visual indicator up here where this LED lights up that D13's gone high, so that'll be my keying indicator while I'm testing with software. I'll probably just take a code practice oscillator and plug it in. Anyway, 0.001 cap, ceramic cap here across the keying output to bleed any RF off that might be coming in or coming out from the Arduino. So the lid closes fine. There is the USB connector protruding very slightly here. So I can just plug the USB cable right in and that'll power it. Keying output, straight key input, paddle input, and speed. So this will sit up behind my radio and I'll just reach back and adjust the speed if I want to and be able to run all of my keys with one. Well, once I finish the software. Now that's what's next. I'm going to take this upstairs, plug it into the computer, and start working on software. Alrighty, well, we've got the hardware done. And now I'm sitting here at the computer and I'm ready to start coding. So I'm going to plug in the, well, first off, let's take a look at the computer screen. Now this is under Linux. Windows is a little different. When you plug in an Arduino, you get a COM port, COM 3, 4, whatever. Depends on how you set it up and you've installed your drivers for. Linux, you don't have to install any drivers. You just plug it in and it shows up. So a quick glance at the computer screen here, and you'll see that I have the Linux dev or devices directory open off the root. And these are serial placekeepers, TTYS. And there's no USB here. Now, I'm going to plug in the Arduino to USB, and it'll power up when I do. And by default, these Arduinos always seem to come loaded with Blinky, which is or Blink, which is a little sketch that just blinks the LED. I don't know if you can see that blinking there. Back on the computer, as soon as I plugged in the Arduino, TTY USB 0 appeared. That's the serial port for the Arduino. That's what we'll program it with. Now I thought I'd take this opportunity to show you the Arduino programming environment. So I'm going to launch it. First time I ran it, so it was complaining about not having a sketchbook folder. This is the development window for the Arduino. Now the first thing I'm going to have to do is I'm going to have to tell it what board I have and what port it's connected to. So I'm going to come up here to Tools, Serial Port, and I'm going to choose that TTY USB 0. And then I'm going to come up here and I'm going to go to board, and I have an Arduino Nano with an ATmega 328. So I'm going to choose that. And now I'm configured, and down here it says Arduino Nano and what port it's on. So I am ready to program. As an example, let's see, we've got examples in here. I'll reload Blink. So here's the source code for Blink. I can check it to verify that it's coded correctly and there's no syntax errors by hitting the check button. It will do a compile, done compiling, and it'll tell me the size of it if everything is good. If there was an error, it would tell me there was an error. To upload it to the Arduino, I simply click this arrow, and when I do, I'm going to hold the Arduino up to the camera. When I click the arrow, it uploads it, the light goes out for a second, and then it starts blinking again because it loaded the Blink sketch and everything is good. So that's the Arduino environment, and it's that easy to compile and upload something to the board. But I need to write the code, and I'm starting with a blank slate. So this is going to take a little while. I'm not going to force you to sit here and watch me typing all the code in, but I'll come back to this when I'm ready to do some testing. And we'll hook my paddles up to the keyer and test it out as I write the code. So here we go. This is the fun part. Well, I spent about 8 hours yesterday working on the code for the keyer, and I've got it working reasonably well. The only thing I have not yet implemented is memories, but we'll get to that. I figured I'd give you a demo of it since I'm pretty happy with how it's working now. I've got it tucked back here behind the radio with the lid open so you can see the light on the Arduino on the inside. And I've currently got it hooked up to the Kenwood, and I'm on 10 meters with the power turned all the way down. So the band is dead, so I can basically do what I want here without worrying about interfering with anybody. And as you can see, it works. The software was a nightmare. There's a lot involved in a keyer as far as timing goes, in reading paddles especially. Paddles are switches, and they need to be debounced either through hardware or through software or through both. And I did it through software, which basically is just timing. I'll talk about the software at the end of the video here. I figured I'd just get into the demo for those of you that just want to see it work. So as you can see, it works fine with the paddles. It also has a through for the straight key. So I could use the straight key or the paddles as I wish. And on the computer, I have a terminal running. Now the Arduino, when you plug it into a computer, creates a serial port. So I just connect the terminal to that serial port, something like HyperTerm on Windows, like you would use to talk to a modem. And with the terminal running, I can type as well. Turn that up. So I can send by the keyboard, by the paddles, by the straight key, or any combination. All without having to move any cables around or switch anything around. The only switch I've got is I have the output from the keyer coming to a little toggle switch here, so I can disable it, switch it over to the Yaesu, or switch it to the Kenwood. So the only thing I have to do is flip a switch depending upon which radio I want to do CW with. And I'll zoom in for a little close-up of the keyer here, tucked back in there in its little Altoids tin, all nice and neat. and another series of E's. So as you can see, we have a nice tiny little keyer. All right, now for the rest of the video, I'm going to talk about the software. So I'll switch over to the other computer here, and we'll show you a flowchart and the software source code, and I'll talk a little bit about that for those of you that are interested in it. Now, the entire project I'm going to post on my blog, and I will include a link down in the description of the video where you can download the schematic and the source code and build your own. The component count is very, very small. It's an Arduino Nano, one transistor, a few connectors, and a pot, and one resistor. So minimal hardware count. It's all done in software. The Nano costs about $5. The rest of the parts you might have $8 or $10 in, and you can have your own keyer. So there you go. Okay, now to the software. Okay, we're here at the desktop computer. So let's have a look at the software. So here's a simple flowchart of, it's very simple, overly simplified flowchart of what the software looks like. Most Arduino sketches will have a single loop that just runs over and over again. You've got a setup section, and then you've got a loop that just runs and runs and runs and runs, and you have to do everything within that loop. Timing on a keyer is so incredibly touchy. When you read paddles, you've got sliding windows where you can read the paddles. You know, this loop is going so fast. It's literally running hundreds and hundreds of times a second. So if you just read the dot paddle and sent a dot, just tapping the paddle, just a little tap, would result in 30, 40, or 100 dots being loaded into the buffer because the loop would run that many times through in the amount of time that you tapped the paddle. So the way that I got around that was sliding windows of time. I know that I want to be able to load one more element while I'm sending one. So if I'm in the middle of sending a dash, I want to allow myself to buffer or stack one more press. That way you can press the dash paddle, and before the dash is done sending, tap the dot paddle and know that that dot is going to be sent, that it got read and it's going to be sent. So I use that idea with sliding windows to read the paddles, where I would had a buffer, and I would allow myself to load one additional event into that buffer. So that's how I got around the problem of reading the paddles when the loop is running so fast. And it's basically a real simple structure. The initialization area sets up all the variables, and it starts an interrupt handler, which I'll talk about in a moment. This was very cool. I'm multitasking on the Arduino. And then we read the inputs, like the speed control pot, and we set up values that we use to calculate the dot and dash lengths for the speed that we're running at. We read the paddles and load a buffer with the events. You know, was the dash paddle pressed? It was. Load a dash into the buffer. We check the serial port, see if there is anybody typing anything. If they are, we process the keys and load the buffer. And then we go up and we do it all again. So this loop just runs handling inputs and loading a buffer. Now that buffer is a string, and I load it with minus signs and periods for dashes and dots, and commas for delays. And the comma is a delay equal in time to one dot. So it's a delay between elements. And how does that buffer get processed and sent? Well, that's where the interrupt handler comes in. Timing through this loop varies slightly depending upon what these sections have to do. If there's something typed on the keyboard, it takes a little bit longer to look up that letter, and then the loop runs slower on the next pass. So trying to key the radio within this loop meant that the dots and the dashes would vary slightly in length, and the timing would vary slightly depending upon how fast this loop was running through. I wanted a more consistent, and it was really important to have a consistent dot and dash when you're keying the radio. So what I did was I set up an interrupt. Now an interrupt is, processors have timers, okay? A timer is like an oscillator running at a set frequency, and it can trigger what's called an interrupt every so often. So I set one up that's every millisecond, 1,000 times a second. It's going to interrupt whatever the processor is doing over here and tell it to go execute this code. So it doesn't matter what my loop is doing, 1,000 times a second, this loop will run consistently, precisely. Every 1 millisecond, this loop runs. So what I have is I have a loop here that is running at a very precisely controlled speed. So I can set up all my timing in here and know that it's going to be accurate. Now it runs through 1,000 times a second. So the way that it has to work, it can't just key down the transmitter, wait for the duration of a dot, and key it up. Because that would be 50 milliseconds or 100 milliseconds, depending upon the speed of the code you're sending. And this thing is going to run every millisecond. So it uses flags to know what it's up to. I set a flag when I'm actively sending called active. And the first thing this does is it checks to see if active is flagged. If it is, we're already in the process of sending, so we don't need to do any of this. And then the other thing I have is a counter that counts milliseconds. So let's say we're at 25 words a minute, so the duration of a dot's about 50 milliseconds. I would set that counter at 50 when I started sending the dot. And then every time through the loop, I'm active, I'm sending, okay, decrement the counter by 1, check the counter, is it at 0? No, then we're not done sending, that's it. Next time through the loop, are we active? Yes. Decrement the counter. Is the counter at 0? Oh, it is. We reached 0. So it's time to unkey the transmitter and clear the active flag, and then we're ready for the next pass. And the next pass, anything to do? Oh, there's an event in the buffer. Okay, we've got an event to handle. Let's handle it. Is it a dot, a dash, or a delay? Process that. Set the active flag, key the transmitter, and remove that event from the buffer and load the counter with the correct number of milliseconds for a dot, a dash, or a delay. And then back through the loop again. So this interrupt handler is always running 1,000 times a second. Anytime that I want to send something to the transmitter, I just load characters into that event buffer. And as soon as I load them into the buffer, this thing starts handling it and keying the transmitter. So transmitter keying is completely taken care of. Timing is precise over here. I don't have to worry about that. I just load the buffer with events. And that's how the program works. Let's look at the code. Here is the actual sketch, the actual program. It's not neat and tidy. I'm not really a programmer. I sort of figure this out as I go along. When I used to program, it was on the Commodore 64 back in the early to mid 80s, and it was machine language. So this is a little different, but I figured it out. I learned it as I went. I've done Arduino programming a few times here lately. In fact, the opener to this video was an Arduino drawing letters on an oscilloscope in the XY inputs. So that was something I just modified somebody else's program for. This one I wrote completely from scratch. This is mine. So here's the initialization section. We're setting up all the variables that we're going to use, and I've commented them. These are the pins that the Arduino is using for this project. Pin A7 is the analog input pin that we're reading the speed on, and that's a pot that's varying that from 0 to 5 volts. I'm using pin 4 and pin 2 for the dot and the dash in, and pin 13 for keying output. I use 13 because it has an LED on the Arduino connected to it, so I had a visual cue while I was working on the program. You could use any pins that you wanted. If your circuit physically lays out differently and you want to use different pins, just change them here. If you want to reverse the dot and dash on your paddle, if you're a lefty, just reverse them here. You just choose these labels are the references the program uses. When it wants to read the dot, it references dot in. So whatever number is here is the pin it's going to read. These are a bunch of variables I have to use throughout the program. You have to declare them in Arduino Sketch. And then here is the initial startup routine, the setup routine. we set the pin mode for key out, the keying pin, to output and immediately write it low, so we're not keying the transmitter. When you first power this up, there'll be a short little keying action before this command runs of about a fraction of a second, and then this turns off the key. So the first thing we do, unkey the output, and then we're setting up the pins. Our pin modes for the dot in and dash in are set to input, and then they're written high, which turns on their internal pull-up resistors because our paddle is grounding them, so we need to have them in a high state. So we do that right away, and then we initialize the serial port. Now, here is the interrupt handler being set up. This is setting one of the timers in the Arduino to call this interrupt handler every millisecond. And then here is the handler that's doing all the keying work. And it's checking to see if there's anything in this event variable, which is the buffer. Is it greater than 0? Do we have anything to do? Are we already active? And if we are already active, if this does not equal 0, meaning we're active, then this just bypasses everything pretty much down to here, and we go back through the loop again. No, wait, no, it bypasses it down to here, sorry, where we're active. We're already active, so we reduce our delay counter. We check to see if we're done. If we are done, we set active to 0, and we unkey the transmitter, and then we remove that character from the event buffer. So if we are not active and we have something to process, we come up to here and we check the first character in the event buffer. Is it a dot? Yeah, we turn on the key, we set the delay to the dot length, and we set the active flag. If the event character is a dash, we turn on the transmitter, we set the delay to the dash length, we set the active flag. So you can see it's pretty straightforward. Is it a comma or a delay? Do we need to delay between elements? Sorry, I scrolled. Now this paddle buffer 0, this is part of my sliding window for sensing the paddles. When we're done sending an element, so we're starting a delay, that's when I enable the ability to sense another key press on a paddle. And we set the delay to a dot length for our delay, make sure the transmitter is off, and set the active flag to 1. So that's my interrupt handler. This is running 1,000 times a second, and it's handling keying the transmitter. And then we've got the main loop. First thing we're doing is we're reading the speed from the analog pot here and doing a little math to give us a range of 50 to 200. And that's going to be in milliseconds for keying the radio. And that's going to be the dot length. And then we set dash length to 3 times the dot length. So we read the paddle, or we read the pot, we set our dash and dot length. That happens every time through the loop. So it'll respond to speed changes instantaneously. I set the speed by holding down the dot paddle and rotating it until it sounds about the right speed that I want. And then we're doing the nasty work, reading the paddles. This drove me nuts, figuring this out here, getting this right. These sets of if statements here, from last dash state up to here, this is debouncing the switch. When you close a switch contact, it doesn't simply switch from off to on instantly. As those contact surfaces come together, it gets very noisy for a brief period of time. As you can see here on the oscilloscope, I'll close this switch. It looks like it's just a transition from off to on, but when we zoom in on it, you can see that it's a very noisy transition. This software is running so fast that it actually senses those switches several times during that noisy period. So what I've got here is basically a window of 40 milliseconds. The switch contact has to change its status for a total of 40 milliseconds before I decide that it has changed. I experimented with that value. That turned out to be about the cleanest and allowed me to send error-free without any debounce or without any false triggers, no extra dots or extra dashes. Let's see. So we read the dash pin, we read the dot pin. That's pretty much the same code, just different pin numbers and loading a different variable, dot state and dash state. Then we do our tests. If dash state is 0, meaning it's been grounded, it's been pressed, I've pressed the dash paddle, I can only buffer one event at a time, or 2 events total, right? You don't want to send ahead too far. That could get confusing. You could end up, well, it'll throw you off. It's okay to buffer one ahead. So if I hit the dash paddle, it starts sending the dash, and then I hit the dot. I can buffer that dot before the dash is done, but I don't want to buffer more than one. Believe me, it'll throw your brain off. So event length is less than 1, meaning I've only got no more than 1 item in the buffer. Then we're okay to load the next event from this dash. And here's the paddle buffer that remember is over on the interrupt handler. So this is if the interrupt handler is done sending the last element and it's in a delay or it's just keyed up and waiting. We make sure that we're done sending that last element before we load the next element in. If I didn't do this, I would end up with 2 or 3 dots loaded when I just tapped the paddle. That's the sliding window that I needed to have to organize the timing, and believe me, it was rough getting to this point. So let's say that we're in the clear. The last element was already sent. We've got enough room in there to load another item in the buffer. So we go down here and we take event, which is the string that's our buffer, and we add to it a dash and a comma. So we're loading the next dash into the event. Send a dash and then delay 1 dot length. And set the paddle buffer to 1 because we just told it to send an element, so we're setting that buffer to 1. And it'll get set back to 0 once that element has been sent. So that's the tricky part there. Using that buffer flag to control timing made all the difference and finally allowed things to work properly. And then we basically duplicate the code for the dot state, for reading the dot. Same ideas. Everything's the same here except that we're doing processing dots. Now, keyboard routines. This is basically one big test of cases for reading in the serial. We check to see if anything is at the serial port ready to be read. Did I type a key, basically, on the keyboard and send it in through serial? We take that value of that key, I write it back out so you can see it echo on your screen when you type it. And then this switch C means we're going to choose which one of these lines to run based on this value of C. In the case that it's a value for the letter A, load the event buffer with the elements for sending an A and break out of this loop. In the case that it's a B, load the event buffer with the elements for a B and break out of this loop. And each one of these has to have an extra dot length delay for the extra space between characters, which is double the space between elements, you see. So basically it takes the character that you just typed on the keyboard and it runs down this list. It finds the match, loads the event buffer with the elements for that match, and then breaks out of the loop. Or breaks out of this while loop that's handling serial. So if I type multiple characters, they all just get stacked into the event buffer, and that interrupt handler will go through it a character at a time, processing it and keying the transmitter. So that's basically the software. It doesn't look like much, and but it took me 8 hours to write because of that timing with the paddles. That was really quite something. So I will publish this up on my blog, and I'll link it below. And I'll draw up a schematic, but I mean it's really simple. There's nothing much there, but I'll go ahead and draw a schematic up, and I'll put it on the blog post as well. It might not be there right away under the video, but it will be there by the end of the day today when I'm filming this. I'm probably going to post the video around noon. So if you came back and you saw this and you want to go back and get that blog entry link, come back later in the day or tomorrow, and it'll be there and you can click on it. And it'll also be published on the Facebook page with the blog entry link, so you can go and download the information in the software and build your own keyer. Pretty easy, simple hardware. I've done the hard work here, so have fun. Thanks for watching. If you enjoyed the video, don't forget to give it a thumbs up. Also, if you're not already a subscriber, click to subscribe. Join us on the Facebook channel for discussion about the videos. And if you'd like to help support this channel, please click to support me on my Patreon page.